Hey everybody, it's Dr. J, and yes, today we're talking about reaction quotient. Let's talk about chemistry. Equilibrium constant, we understand that we're using them when we're at equilibrium. All right, and we only can use K. Now, what happens if we're not at equilibrium? Well, this is where we have to use our good old friend Q. All right, so it's another letter. It's another letter, everybody. Okay, we're using another letter. Yes. Okay, so reaction quotient. Okay, so basically, it's going to have the same form as our K, but we're able to use this when we're not at equilibrium. Okay, so anytime we're not at equilibrium, we're going to be using Q. All right, if we're at equilibrium, use K. But basically, right, Q is going to look something like this, right, to where it's still very similar. Products of a reactants, but instead of equaling, right, it to K, it's equal to Q. All right, and that's due to it not being at equilibrium. So for our Q, we're still going to have our products of our reactants with our coefficients being raised here. So literally exactly the same. The only difference is we're not at equilibrium. That's it. So we have to compare our Q to our K in order for us to basically know, right, which way we're going to reach equilibrium. Now, we got three different scenarios here. If our Q, right, is bigger than our K, our reaction will proceed the fastest in the reverse direction. So basically, our products are decreasing, right, but our reactants are increasing. All right, we're going in the reverse way. All right, we're going in reverse. If our Q is less than our K, right, so our reaction will proceed the fastest in the forward direction. So basically our products will increase and our reactants will decrease. And lastly, if our Q is equal to our K, our reaction is actually at equilibrium. So our products and reactants are not changing at all. We're at equilibrium. So if I look down here at this example, we got our B and A, right? And then it's equal to Q, so products over reactants. And then what we have here is our Q or K, right? And then we have our concentrations on our X. And then over time, what do we see here? As we go, right, from A to B. A to B. So we're making our B, our product. As we make our product, what do we see about our Q and K relationship? Well, our products are increasing, our reactants are decreasing, right? We're making products. So in this case, our Q is going to be less than our K. At this point, right, and I got the big graph over here, the big thing will show it what's happening here. But at this point, if our Q is equal to our K, right, at this case, 1.45, right, we reached equilibrium. There's no change occurring. So our products and reactants will not change. But let's say after that point, right, we continue to go up. Now we're going to reach a point to where now, all right, my Q is actually going to be bigger than my K. All right, in this case, my Q being 2.55 bigger than my K, which is at 1.45. So if my Q is bigger than my K, my products are now decreasing because, right, we're going in this reverse direction now, right? Our reactants will increase. So remember, everybody, the goal is to get to equilibrium. That's the goal. So this is why, right, my Q is going forward because we're trying to reach equilibrium. We're trying to get there. My Q goes in the reverse direction now because, oh, I realize I need to go back to get to equilibrium, right? That's where I'm trying to go, right? And this is what we see here in this graph and really how we're going to be using our reaction quotient going forward.